We're now getting into section 3.3, and 3.3 discusses the notion of different parts of the function where they might increase or they might decrease. So I want to identify portions of the function that are increasing versus portions that are decreasing versus portions that might even be constant. And first I want to define what increasing and decreasing intervals are. We'll draw a picture to take a look at what they look like, and then we'll use calculus to nail it. We'll actually find the very intervals that the curve increases and the very intervals where the curve decreases. It's not something you can really do accurately without calculus. So to get started, I want to define what an interval that increases or decreases actually is. A function, f of x, is increasing on an interval. If for any two numbers within the interval so we'll say x1 and x2, where x1 is the smaller of those two numbers, function is increasing on the interval if for any two numbers within the interval where the first one is smaller than the second implies that the y value of the first is also smaller than the y value for the second. So simply interpreted, that means when we move from left to right on our function, our y values are getting bigger. And this is for any two x's in the interval. So that means it's forever increasing in this interval. A function is considered to be decreasing on an interval same situation if for any two numbers within the interval, and again, same two, x1, x2, where x1 is still the smaller of the two x values. This implies on a decreasing interval that the f of x1 is actually bigger than the f of x2. And that really says that as you move from left to right, we're still moving from left to right as we normally do. Now the y values are starting big and they're getting smaller. And this is throughout the entire interval, so x1, x2 can be any x values within the interval. And finally, one more definition here, and that is a function f of x is constant on an interval if, same thing, you can pick any two numbers within the interval same two numbers, x1, x2, and why don't we make the same restriction here? We'll make x1 smaller than x2 so that we're moving from left to right. And this implies something different, that the f of x1 is actually equal to the f of x2. In fact, all the y values within this interval are equal. Okay, so that's the definition of the three different types of behavior we can have within a specific interval. And we will break the entire real number line up into intervals from A to B, and then we'll say, okay, in this little section, does it increase? Does it decrease? Or maybe it stays constant. If we want to draw such a picture, it kind of looks like this. Well, let's break it up, guys, into intervals. So let's make this x1. Let's make that x2. Let's make this x3. And I would say this is an interval in which we continuously are decreasing. And if I were to call that interval out, that's for, in interval notation, this would be my interval. Now this seems to be an interval in which my y value remains constant, and if I were to call that interval out, that would be x1, x2. Here's my increasing interval, and that interval would be x2, comma, x3, not an ordered pair. This is interval notation. And finally, we do have one more decreasing interval right here. And that one would be called out in interval notation as x3, comma, infinity, like that. So there it is, both in words and also graphically. Areas on the curve where we get increasing and decreasing. Now comes the test. What is the test? The test for increasing, decreasing is, notice that if we went up here to the increasing interval, that no matter where you sampled the derivative, f prime, and I'm sorry, that's supposed to be decreasing, right? Decreasing interval, so decreasing. You go into a section that's decreasing, f prime is less than 0. It's negative for all x's within the interval. I'll draw one for you here. Here's an f prime getting a slope of a tangent line. All my f primes, all my slopes are negative. For an interval that's constant, every single one of my f primes within that interval is 0. They're all flat, 0, 0, 0, 0. And then finally, let's go to the section that's increasing now. So come on up here and draw some derivatives, some slopes of tangent lines, and those are all positive, all of them. So f prime of x is greater than 0. And these are for all the x's within those intervals. So that's the test. The test is f prime remaining positive? Well, if it is, then you're in a zone of increasing function. Is f prime remaining 0 throughout the entire interval? Then you're in a zone of constant function. And if f prime is negative throughout the entire interval, then you're definitely in a zone where the function's decreasing. Now, definitely a good idea to look back here for a moment and see where the shift took place, where the changes occurred. Well, they occurred right here, at critical numbers. So critical numbers leave hills or valleys behind, and those are the opportunities to change from increasing to decreasing. By the way, these are all critical numbers, believe it or not, every single one in there, because they're all f prime 0, f prime 0, so there's just a lot of critical numbers in here. But the change will always occur at a critical number. But does it always occur at a critical number? That's the question. Let's take a look at another curve. Put an asymptote right there. So I'm going to draw a curve here that looks maybe something like that and then shoots off the page. And then it comes back down and maybe it's even symmetric and does something like that. So let's take a look at this thing. Zones of increasing and decreasing, intervals where it increases or decreases. Here's my critical number here. That's my first one. Here's another critical number right there. That's my second one. Here's a third critical number here. And finally a fourth critical number here. These are the only true critical numbers on this particular graph because the slope is supposed to be either 0 or undefined. Now I will say that the slope is undefined at this asymptote. If anything, it's a vertical slope. So why isn't that a critical number? critical numbers are defined where the slope is either 0, f prime, or f prime is undefined. But critical numbers need to have a function value in place. The function has to be defined there. There should be a coordinate there. There is no coordinate here. Now, let's take a look at where the curve increases and decreases. It's increasing here. It's decreasing here. It's increasing over here. And it's decreasing over there, increasing, and finally decreasing. So, where are the opportunities to change from increasing to decreasing? That would be at a critical number here. Where are the opportunities to change from decreasing to increasing? At critical number here. And also the changes occur here. But also take a look at the asymptote. An asymptote is also a potential site of change. So we need to look at that. Now, if you weren't a calculus student, you wouldn't know where these relative maxes and mins were, so you wouldn't actually know the interval boundaries. But looking at this diagram, I now know where the boundaries are. The interval boundaries are either at critical numbers or asymptotes. Those will pretty much be the only places you're going to find the curve having the capacity to switch from increasing to decreasing. Critical numbers or asymptotes. Okay, so let's try this. And the way to do this is to determine the intervals in which we have increasing and decreasing. And the way to do that is you've got to find these critical numbers and asymptotes. So let's do an example problem, and I'll show you how we piece this together. First thing to do is to find those critical numbers. So let me give you a function here that we can work with. And I'm using one of the examples in the book. F of x is equal to x cubed minus 3/2 x squared. I don't think we're going to find any asymptotes on that particular problem, so I'm not really worried about that. But I do want to know what my critical numbers are, so that would be step one. Find those critical numbers. Find the critical numbers. And how do you do that? F prime equals 0, F prime equals undefined. So F prime is 3x squared minus 3x, and I want to know when is that going to be equal to 0. Factor out the 3, factor out the x. When is that equal to 0? There are some people that tell me that 3 is a critical number. That is not true. If I put 3 in, I'm going to get 3 minus 1 is 2, times 3 is 6, times 3 is 18, not 0. In fact, 3 is irrelevant to this problem. Let's get rid of it. So my critical numbers are x equals 0 and 1. Now, remember the rule on critical numbers. These also must make the function defined at those values. So if I put 0 in, I get 0 back. That's fine. If I put 1 in, I get -1/2, which is a value. So that's fine. So I can really call them truly critical numbers. Now, to be thorough with critical numbers, you must also do this. The next thing we do is, well, it's really not a number because we're doing number 1 still. We want f prime to be undefined. But look at f prime here. Will that ever be undefined? I don't think so. To be undefined, you need to divide by 0 or take the square root of a negative number. Those are the two top reasons why something will become undefined, neither of which will happen. So this doesn't happen, so we won't get any critical numbers from this. Okay, we've got our critical numbers. So what do we do with those critical numbers? Now we're on to step number 2. Step number 2 is to establish the intervals. And here's how it's done. I want you to take the entire number line from negative infinity all the way to infinity and use your critical numbers and your asymptotes as slicers. So we have a 0 slicer here, a 1 slicer there, and use them to slice up your domain of all real numbers. So the first thing we're going to do is establish that there really are 3 intervals. The first interval is right here, all the x's that are less than 0. The next interval is right here, all the x's between 0 and 1. And the last interval right here, all the x's that are greater than 1. Now, there's some behaviors going on in these 3 intervals, and I'd like to investigate what they are. And the way to do that is to go back to the definition. The definition states that every x value in a particular interval will have the same behavior, either increasing, decreasing, or constant. So we don't need to test every single one of them. We need to test just one. So I want you to have a representative to stand in for that entire interval. Just pick any representative that you like. So we're going to call this a representative, okay, that stands in for the entire interval. And that means pick one. So I'm going to just pick a test value of x within the interval, and probably the best one would be just that one right there, -1. Let's pick a representative that lives in this interval. Well, you can pick any one you like, but probably the best representative is the one in the middle. And then let's pick a representative over here. Let's pick 2. So there they are, our representatives. Now the next thing that we do is that we sample the derivative at the representative. What I need is to actually evaluate f prime at -1 to see what I get. I actually want to evaluate f prime at 1/2 to see what I get. I want to evaluate f prime at 2 to see what I get. Now, the only opportunity to change from increasing to decreasing is right there at those critical numbers. So that means that if I do this sample here and f prime comes out negative, negative means negative slopes means decreasing, it will decrease for the entire interval. So what are we going to do here? We've got to go to f prime. Now, as a reminder, f prime is right here. In fact, I factored it, so I might as well show it as a factored f prime, makes it easier to plug into. So -1 goes in, you get -1 minus 1 is -2, times -1 is 2, times 3 is +6. Let's put the 1/2 in. 1/2 minus 1 is -1/2. -1/2 times 1/2 is -1/4, times 3 is -3/4. And then put the 2 in. 2 minus 1 is 1. 2 times 3 is 6. That's +6. Now, the numbers don't concern me too much. They tell me how steep the curve is. This is very steep here and not so steep there. But this is what I really care about, the plus or the minus. So now identify these intervals as either increasing or decreasing. That is definitely an interval of positive first derivatives. Positively sloped tangent lines indicate that that interval is increasing. Negatively sloped tangent lines indicate that this is an interval that decreases. And again, here's a positively sloped tangent line. So here it is. For all x's less than 0, we must have a curve that decreases. For all x's between 0 and 1, the curve goes down or decreases. And for all x's greater than 1, we have a curve that increases. Now, if we want to be certain about this, one great way to do that is just graph it. And let's take a look at what the graph might actually look like. So I'm going to fire up my little graphing calculator, which is on my computer here, and see if that can tell us what's going on. So let's take a look here. It's a great program that does just graphing. It's called Desmos. So let's take a look at this. It's called Desmos, D-E-S-M-O-S. So all right, here I go. I can just type in y equals x cubed minus 3/2, or 1.5 if you like, or 3/2 x squared. And let's take a little zoom in here on our intervals. Well, as predicted, all x's less than 0 in this region, we have a region in which the curve is increasing. In fact, you can see it's pretty steep here, okay? Also, as predicted, from 0, x equals 0, all the way here to x equals 1, we have a region of the curve that's decreasing, and it's not very steep. And then finally, from x equals 1 all the way off to infinity, you definitely have a portion of the curve that's increasing. So that's a great thing to do, to take a look at whether we got it right or not. So you want to make a table. The first thing you want to do on this table is slice. And the slicers will be either critical numbers or vertical asymptotes. You need both of these because vertical asymptotes have the capacity to change from increasing and decreasing. Hey, another thing to note, and that is that critical numbers and vertical asymptotes don't guarantee a change. They don't. So you must sample the derivatives and then check it out underneath whether they're positive or negative. There are functions that you'll get critical numbers for, and it'll be increasing, 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 and that function is continuously increasing. In fact, if the function is continuously increasing throughout the entire domain, we call that function monotonic. It monotonically increases. And if the function decreases throughout the entire domain, we call that monotonic as well, monotonically decreasing. Let's try another example to find sections of the curve that are increasing and decreasing. This is a great one right here. So let's try this one. This curve is defined by this function, f of x is equal to x squared minus 4 raised to the 2/3 power. First thing is, are there any vertical asymptotes? Is this function, will it ever be undefined? And the answer is no. There's no division, so you'll never divide by 0. And you see the power here, 2/3? The third down in the bottom, that's a cube root. And cube roots are okay. You can take the cube root of a negative number and get a real number back. It's square roots that we're concerned with. And fourth and sixth and any even root can be a problem if you put a negative inside. So this thing will always be defined. So the domain, I think, is all real numbers, right? We'll never take the square root of a negative number. There's no square root. It's a cube root. We'll never divide by 0. That means there are no vertical asymptotes. If there is a vertical asymptote, you do need to take that into consideration. All right, first things first, we need to find our critical numbers. How do we do that? Critical numbers, f prime equals 0, f prime equals also undefined. Now remember, a critical number where f prime is 0 is either a hill, a valley, or a little flat spot like that. These are critical numbers right here. These are the f prime equals 0's variety. F prime equals undefined while also f of x is defined. What do those look like? Well, when f prime is undefined, like infinity or just not working, you're not getting a value, but the function is and has a point, those are sharp corners. And we very much need to be looking at these because notice that changes from increasing to decreasing. So we've got to look at those. So let's make sure we don't forget these. Okay, let's do f prime. Chain rule. Very important on this problem. We check off the 2/3. The 2/3 comes down. I deduct 1 from my exponent. 2/3 minus 3/3 is negative 1/3. Copy, please. Don't go too fast with this chain rule. Arguments never change. Okay, that we only checked this off. Now you got to check that off. Well, the derivative of x squared is 2x. Minus 4 is just a constant, so that's plus 0. The 2's join up, so f prime is going to be 4x over 3, and this can drop to the bottom, can't it, because it has a negative exponent. And that becomes 1/3 power. That's just a cube root, like that. Now, I'm going to leave it just the way you see it, because I want to investigate both styles of critical numbers. How do you determine f prime equals 0? How is a fraction equal to 0? If you just say that the numerator equals 0, I think that's going to get us to get that fraction to be equal to 0. If you say that the denominator is equal to 0, I think that will get us to where we want to be, where the f prime is undefined. That makes sense, right? So you have to do both. Let's do both. Okay, so we're coming up with boundaries for our increasing, decreasing intervals. Let's start with the first one. F prime equals 0. I'm looking for hills and valleys and flat spots. That's what I'm going to find when I set f prime to 0. Now remember, on a fraction, you just set the numerator equal to 0. That would be 4x equals 0, and x equals 0 is a critical number of this flavor up here. Next, what would cause f prime to become undefined? And when f prime is undefined, you get these sharp corners. Okay, those are certainly places of interest, and we did say that one way to do that is just set the denominator equal to 0. So our denominator is 3 cube root of x squared minus 4. When is that equal to 0? Let's find out. So divide by 3, divide by 3. So cube root of x squared minus 4, when is that equal to 0? Cube both sides. So x squared minus 4, when is that equal to 0? Add 4, add 4. And so x squared, when are you equal to 4? Well, twice, plus and minus 2. Two more critical numbers. And think about how you got them by setting f prime undefined. So these are sites of these spiky corners of some kind. You can very well bet that when that happens, we're going to get a change from increasing to decreasing on those sharp corners. All right, how do we set this table up again? Line up your critical numbers as slicers. And I want you to slice up the entire domain of real numbers. The first thing you're going to want to write down is the interval. These are all the x's that are less than minus 2. These are all the x's between negative 2 and 0. These are all the x's between 0 and 2, and these are all the x's that are bigger than 2. Next thing, you need a representative. Pick one in each interval. I'm going to pick minus 3 for that one, minus 1 for that one, positive 1 for that one, and positive 3 for that one. Next thing, f prime at your representative. You're sampling the increasing, decreasing within that interval. Now, in order to do that, I think we need f prime back to help us out. So f prime is right up here. So let's sample. Negative 3 goes in, and what are we going to get? Well, I'll do that on a separate piece of scrap paper here. So I'm going to put in my negative 3, and I'm going to get 4 times negative 3. I'm going to get the cube root of negative 3 goes in. I get 9 minus 4 is 5. And, well, minus 12 over 3 cube roots of 5. And if you want to rationalize this, you can. But I don't really care what that number is. I care that it's negative. That tells me that this is a region in which the curve must be decreasing. Okay, next, let's do -1. That would be the next one here. So I'm going to plug -1 right up here, and I get 4 times -1 all over 3 cube roots of -1 squared is 1 minus 4 is -3. Now, you're allowed to take the cube root of a negative number. That's not a problem. In fact, you can factor the negative out. It does work. And that reveals something to me, and that is this derivative is positive. So this derivative is a plus 4 over 3 cube roots of 3. I'm not even going to bother with simplest radical form because that's all I care about. You're in a region in which the curve increases. Okay, now let's do x equals 1. So x equals 1 now needs to go in to my derivative, and that would be 4 times 1, 3 cube roots of -3 again. That's all I really care about. This is definitely a region where the curve starts decreasing again. And finally, let's put the 3 in there. And just to save, save you some time, you would get positive 12 over 3 cube roots of 5. Symmetrical, it works the same as that one. So we have a curve which decreases, increases, decreases, increases. Now, I need you to remember what these critical numbers were, and that is that this one was the site of a sharp corner. What do sharp corners look like? Well, decreasing, sharp corner, increasing. That's what that should look like. This is a sharp corner here at 2. Decreasing, sharp corner, increasing. That's what that one should look like. And this is a hill, valley, or flat spot. Well, it's certainly not a flat spot. It goes from increasing to decreasing in a smooth way. So that must be a hill, and that is what we would expect to see on this curve. Now, the best way to really verify all that is to graph it. So let's go ahead and, again, get our graphing calculator up, and let's take a look. So the curve here, again, is y equals, and it's x squared minus 4, all raised to the 2/3 power. Let's take a good look at this thing. Pretty wild looking curve, huh? Almost looks like half a circle, but actually we got everything we expected out of it. We got the sharp corner here, we got the sharp corner here, and we got the top of a hill here at x equals 0. So that's pretty cool. So derivatives will let you peek in on the behavior of the function, increasing versus decreasing. What you want to do is make a table. You want to use your critical numbers as slicers to slice up your domain, show me all the intervals, pick a test or representative value, sample the first derivative, and then interpret your results, increasing or decreasing. Now remember those slicers, critical numbers, and I also want you to put asymptotes in there if you have them. For these examples, we did not have them. So that's it for increasing, decreasing. So the next topic that's coming up will be the first derivative test, which actually taps into this topic perfectly. So we'll see you on the next video.